Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about 3D CNC Kinematics. So let's dive right into it. Now, what exactly we are talking about here? Well, we are talking about CNC. Now, how the heck do CNC machines move? You have to understand there is again, it goes down into a rabbit hole, but you have to understand the overlay of it so you can go down into a rabbit hole. So CNC are a machine that simply does three things: move things in X, move things in Y, move things in Z. That's all it does. CNC simply means computerized numeric control. Before we had computers, there was a numeric control system. Yes, it was made in 1950s. And then once we figured out computers, then it became computerized numeric control. Now, that's the beauty of it. It simply allows you to move whatever the tool is, meaning it may be a laser diode, it may be a giant laser reflecting mirror, because in big system, you will find lasers are static and all they are moving is the basically optics of it. Basically, it's being reflected in multiple times and then you're getting things done. So things are moving in three axes: X, Y, and Z. And it's used in almost everything. For example, laser engraving, laser cutting, you can have CNC routing and milling. Yes, they are different. And 3D printers, of course, they use a pick and place machine, which is the backbone of entirety of mass production. So you have to understand CNC is important. The more you understand CNC, the more you understand the world that we live in. It's a here, it's a real, it's backbone of us. So we have to understand it. So let's start with the fanciest looking one, that is CoreXY. Now CoreXY, it has a very unique name, but you have to understand all it does is basically move two axes simultaneously, meaning if you want to move the stool head, you are moving two motors. It's a shared relationship. Generally, based on how machines are, they are generally classified as X and Y axis. And because of the consequence that even if you have to move something directly, it will not allow you to do that. It's like, bro, you have to move both motors. Now, doing that does require a bit more complex mathematics, because you can just design whatever the hell you want, but if microcontroller is not fast enough to keep up that mathematical calculation, it's simply gonna crash. So fundamentally, it does require some beefy hardware. 32-bit microcontroller. Like, can you run it in 8-bit? Yes, but you have to run it slowly so it can crunch through the numbers properly. Or generally, just 32-bit microcontrollers nowadays is very cheap, so it's a very simple thing. However, it does have the benefit, because one motor is not on the axis that will be responsible for this. It's very light tool head, meaning if you have 3D printing heads, it would be very light. If you have just a laser engraver, it would be very light. Benefit of that: quick ramps. Ramp simply means acceleration and decelerations. Now you have to understand this. If you may think, okay, I'm just going to increase the speed by increasing the motor capacity. Yes, it will not work that way. Like, why? Well, here's the deal. In principle, that should work, but here's the deal. There is a law of physics known as inertia, meaning if you have a heavy object, no matter how much horsepower you will put into it, it will take certain amount of time to get into the speed, and then it will take certain amount of time to get down from the speed. So basically, you want it to accelerate and decelerate, it will have a maximum G loading basically. Like, no matter what you do, it has a limitation to it. So how do you make it faster? You make it as light as possible. So you keep the same motor. Let's say you have NEMA 17 motor into it, not the biggest one, just basic NEMA 17, and you are like, hey, how do I make it faster? Make it as light as possible. You will be surprised how quickly, because the top speed will not change, but the acceleration and deceleration will change drastically. That's why every Tom, Dick and Harry wants to make their tool heads as light as possible. Now, these are also very volume efficient, meaning how much of an area that you want to cover, basically moving in two coordinates, and how much area outside of it you have to have for the tools and stuff. It's very efficient, like very efficient, meaning if you have a big print volume, let's say 300 mm or let's say half meter, you'll barely need like 20 to 30% more on all sides. Not even that. Like realistically, you're going to shrink out even smaller than that. So they are very volume efficient, meaning how big your machine would be in order to work to get the workability is very good. That's why like laser cutters generally prefer that. So they are very volume efficient for the size, but they are low precision because belts are taking such a long path, and belts are inherently not a very rigid construction. They are not steel, they are not tungsten or some things like that. So they have a slop to it. Now again, modern belts are really good, especially carbon fiber reinforced one. They are really, really good. But if especially you once to start to make long, like let's say long enough to deal with a plywood sheet in one go, yeah, at that point in time, it's just like lol. It's basically generally used for low precision lasers. Low precision meaning it will have a tolerance that is not the greatest. Now again, if you are dealing with cosmetic things, if you are dealing with things that are like, you know, decorations and all that, which is a very big industry nowadays, more than good enough. Quick. At that point in time, getting things done quickly is far more precious, so people are like, choose that. Same goes with 3D printer. 3D printers are slow. If you do not have a 3D printer, you do not have idea how slow 3D printers are. Like, you will be shocked how slow 3D printers are. Like, it takes 6-7 hours to print something small, like this small, like very small. So in those sort of scenario, having ramps that is like, let's say twice as fast, you can cut down time drastically. So people choose CoreXY. Now it does have a consequence, does require a bit more computational power to crunch that numbers, but is desirable. Then we come to the most common and basic and most robust system, Cartesian style. Now Cartesian style, in simplest term, think of it this way: there is one motor minimum per axis. You have X, you have Y, you have Z. That's it. Each of them have their motor. So for example, for Z axis, there will be a motor behind it that is moving up and down. In this scenario, you have two. Now be mindful, when I specified one motor each, does not mean only one motor. It can easily have two motors per axis, and many times they do. Especially for CNC machine, you will find two motors per axis. So if belt is very long, basically if movement axis is very long and you have a long arm, it will twist. If you're like, it will twist like that. So that's why you generally want to put two axes, so it's very stable. So minimum one, two if you can afford it, or if you need it. For example, if you are a really long fat bed, like let's say 4 feet long or even like 2 meters long, again, you have to have two motors, otherwise it will simply not work. So you have a motor per axis, and it's very oldest and simplest technology, meaning this is what started the industrial revolution in 1950s. This is what created the numeric control, which over time evolved into computer numeric control. So it took its time, but it's the basis of everything. Now you can have built system, basically you can have built-in 3D printers, but you can also go to ball screw. Now that's the interesting part. The moment you touch ball screw, you get rigidity. Now once you have rigidity, meaning you can fight against something. 3D printer has minimal reaction, meaning basically how much energy it has to spend in order to fight the filament that is coming out of it, negligible. Yes, there is plastic, yes, there is some viscosity there, but it's very negligible. Laser, there is no physical contact, so it does not simply care. But the moment you are going even on a wood, if you're carving it, the drill bit is going against wood, action equals reaction, so wood is fighting back. Now that simply means that vibrations, that basically the impact will be transferred into the motor. That motor will transfer it to the caddy. That caddy will move. Basically, if you are bounding that puppy up with something sloppy, it will shake, and good luck getting good result out of it, and there is a very good chance you will break your end mill the moment you touch it. So that's why if you need rigid structure, you can go into ball screws, and that's how all CNC was. That's how you are achieving something like this. You're not going to achieve something this strong with belts. Physics does not stop you, it just becomes too ludicrous to try. So if you want high rigidity for milling or routing operations, people generally prefer this sort of system. Now, because of the low cost achieved, again, it's low cost simply because it's the oldest system. The simplest computers can run it. It's also found in 3D printers, because my 3D printer Ender 3 has this system. Why? It's simple, it's cheap, it's efficient. You don't have to think too much about it. Your microcontroller does not have to overwork with it. So it's super efficient. And metal CNC, there is no other option. You have to, like, the moment you touch metal, even something as light as aluminum, if you are using CoreXY system, you have to go very slow into it, very slow. Might as well, if you're working with plastic, that may be a desirable option, but be mindful, it still would be a bit sloppy. So depending on requirements, people generally do not prefer belts the moment they are going with subtractive manufacturing. So metal CNCs are generally always using screws, and that prefers Cartesian style, because again, screws do not have the tendency to like loop around or do tiny bends. So Cartesian is the base. Now there is a sub variant of Cartesian, that is moving bed design. Now moving bed design is key for subtracting manufacturing. Now if you think like how the heck people used to manufacture complex things like jet engine in 1960s and 50s, this is the thing. Again, this is a computerized version. Just remove computer from it, it will become a milling machine. Now how it's moving? It has the bed that moves in 2 axes. Now Z axis is locked. Now why it's locked? Because you have to understand, if you want to take a small cut from an object, it's super easy. But what if you want to take 1 inch of it? Like let's say this is a steel block, and like I want to remove 1 inch from it. You can do it, very small chip, but again, time is money. You do not have, I'm machining this part, it's gonna take like, freaking 3 hours. Money. So you may be like, what if I make a machine that can do the same job, basically remove 1 inch, but it can do it in few seconds. Tada. Now how does this machine achieve that? Again, reduces the axis. Basically drill bits, things that are doing the work, they are under the most load, so they give the rigidest, hardest architecture to that. So it's Z axis, and it has only one movement, so it does not have to deal with like floating axis, like just one axis, and as strong as possible, as hard as possible, as rigid as possible, just for one thing, Z axis. And then you move the bed around. So this allows very simple structure is Cartesian core structure, only moves basically work tool is only moving in z-axis. It's very slow comparatively speaking, and it's very methodical, meaning you will see people working with it like they're rotating knobs. They will have even gears in those knobs, so it can allow, like, you know, you're doing coarse movement and then you're like, okay, now it's fine moment, now you're taking your time, you're very methodical. These are like amazing, like that's how industrial world was built, using this sort of machine. And they're strong, meaning you have metal, this will just like nope. You have steel, it's like nope. Armored steel, they are ludicrously hard, it's like nope. It's very, very strong. If done correctly, these things are god tier powerful, and like this is the base of heavy industry. Basically nothing else can touch this sort of rigidity. Again, physics is like the less parts you have to move around, the more rigid you can make them. So this is preferred. Moving bed designs are preferred where you need to work with some heavy robust thing. Consequence, it does have very inefficient space, meaning it will consume very large area just to do small thing. That's why you will see the machine, it will look like, oh, it's a big thing. Nah, it can only work in, like, you know, very small things. It is used for heavy operation. If you're working with something strong, something robust, this is your tool. So which design do you use for your machine? Well, it depends on what do you need to do with it. For example, you can have a CNC router as, like, again, the moment you say CNC router, people think of this something this way. Now, this is good. It works well, especially if you have very good tooling structure. You can achieve some really high precision, but these are slow, inherently slow. If you are not dealing with metal, these are amazing. But if you are dealing with metals, like for example, how ULA is using its giant CNC router to mill like giant sections of aluminum, it's very slow. Like, it's like, I'm taking my time. Again, it also have to do that for accuracy purposes, but you get the point. It's like it takes its sweet time, but it's also very space efficient, meaning, for example, many wood carvers who are like you know, processing whole sheet of plywood, they will have a CNC router that is just a bit bigger than the plywood section. Because one master plywood is like, okay, 20% add on each side, and there's like shoot, clamp everything down, routes the thing, put it on the next table. Done. Super efficient, space efficient. And you have to understand this counter relationship. Speed and strength, they generally move against each other. You may have a feeling that, oh, I can just give a bigger motor, I can just, no, physics does not allow you to. That's why I specified. Your ramps will be directly proportional to how light it is. The lighter something is, the inherently more you know, wiggly woggly it is. So speed and strength, they are going against each other. Now, if you're working with laser, you generally will focus with speed. If you're working with very hardened materials, you will focus on strength. If you're working somewhere in between, let's say aluminum, you can go with something like this. Even steel, there are some CNC routers that can work on steels, but again, take your time, be gentle. So be mindful, speed and strength, they are opposite to each other, so you have to balance out based on what your need is. Now, cost is also the inherent factor here, because again, I would love to my Ender 3 to have 2 Z-axis, but here's the deal. 2 motors will cost more money, it will require more parts, it will basically increase the total cost that I have to deal with. I don't like that, so that's why I bought Ender 3, because I could have bought other 3D printers that had dual axis motors, but again, I'm not that rich. So cost also plays in role, because everybody wants CNC mill. But you have to understand, even if your company can afford CNC mill, can they afford a giant CNC mill that has like that kind of work area? Because again, be mindful, how many machines you have in a workplace defines how you know, high your throughput is. If your throughput is low because you can only fit, let's say, 4 CNC mills compared to 8 CNC routers, you will choose 8 CNC router, because that will increase your throughput. Throughput will increase your productivity. So cost is a very serious limitation, and scale plays a key role. That's why if a CNC router is desirable for many scenarios, CNC mill is desirable for other scenarios. If you are dealing with stuff that requires a unique advantage of like CoreXY, you will choose CoreXY. So you have to think about all the vectors before choosing the right algorithms for your system. How the heck you're gonna move X, Y, and Z? 3D printer is one of those things that has almost everything. Somebody actually built a router style 3D printer also for some reason, but yeah, it also exists. So this was my presentation on CNC Kinematics. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me extra disappointment. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.